Hey everyone, how are we doing? Just getting going right here. Let me make the dates a little bit better. Bulk adjust assignments. Get started on some homework here. Get the homework going. Adjust. Edit dates and status. Oh my gosh. Chapter 12. Let's look here. Chapter 12. We're going to put here. And we're going to put this here. Sampling distributions. We're going to put over. Start that next time. There we go. Sampling distributions. That looks about. Otherwise, I'll get one date on it. Is that right? Sampling distributions. Sampling distributions. Sampling distributions. Ooh, there's an error over here. Gosh, we're almost to April. Okay, fixing this up. Okay, that's right there. And then that'll fix this. Okay, so that's where I made the error, I think I did. And the test is on... Yeah, I'd like to have that finished up. Monday. I think the test is on the 9th. The test is on the 9th, so... Doing this right here. Lots of time. Chapter 12. Yeah, let's go to the... That'll be good. Sample distribution stuff. Update all settings. There we go. Okay, let's do some of the homework here. Chapter 12 homework. Is anyone here in the chat? Sent out that announcement, didn't I? Anyone here in the chat? Chapter 12 homework. Get it done. Hey, what's up, Jordan? Let me make sure. Mubot might be here. Good to see you, Tamara. Good to see you, Kai. Good to see you, Jordan. I'm enforcing for. I was wondering if you could use cheat sheet. Yes, you get the one-page notes, front, back. Your notes are there. Kelvin, good questions. Chapter 12 quiz. Yeah. Should we do the homework first? Let's take a vote. Homework or quiz? You're here. We could do the full homework. We do the quiz. So we'll do a vote, quiz, or homework. You're here. I got things resituated. Getting that done. Oh, nice walk. My shoelace kept getting untied. No shoelace. Just untie shoelace. What's going on? Canvas content quiz? Yeah, we could do that next year. People were saying the quiz. We could do Canvas content to start. Canvas content quiz number 6. Might do that. Those are easy to do. Like, we get those down pretty darn quickly. So let's see. We got the hiccups. Had a good peanut butter and banana sandwich. So good stuff. Kai, I think that'd be a good place to start. I like doing those because they're pretty simple. They're pretty easy. Not too hard to do. Canvas content number 6. Due on Friday. Let's do that one here first. How about we do it? Over to the main screen. Okay, we're doing some Canvas content number 6, and we're going to jump into the quiz because there's a lot of quiz questions we can do. A lot of quiz questions. Okay, I saved the previous video. So the first question right here asks us, let's go to the preview on it. I'm getting my notes up. Put in the notes 703 Canvas content number 6, and this is going to be chapter 10 and 12. First question, I need your help with these. Let's do it. The concept of a population is key in inferential statistics. True or false? True or false? The concept of a population is key in inferential statistics. Is that a true thing or a false thing? Is that a true thing or a false thing? The concept of a population, is that key in inferential statistics? What do you think? Need your help here with these. They're tough questions. What do you think? Don't worry about being wrong. It's only a 50-50 shot. If you're wrong, whatever. No one will remember. What do you think? A concept of... Yeah, it's very true. Good answer is Kai right there. It's very, very, very true. It's because... statistics, why do we call it inferential statistics? Like if you go out and sample something, which will give you statistics, you use statistics to make what about populations? Like why is it called inferential statistics? Because that's why a population is key to it, because it's the other part of it, because you gather samples which give you statistics You make inferences into a population of interest. So that's why the population is so important, is because we're going to make inferences into this population. This is very, very true. When a sample is said to have the corresponding characteristics, we call it a what sample. Like when your sample has the characteristics of the population you care about, you've collected a what sample. So there's the answers down below. We've never mentioned bifurcated. Like split off, bifurcate. So we've never mentioned that one. Which of these sounds about right? When a sample is said to have the characteristics of a population, you've collected a what sample, which is the goal of statistics, is to collect these sorts of samples. These are the kinds of representative, representative sample. Bifurcated, just a random word on there that we put. And biased is when your sample does not have the characteristics. Insignificant deals with p-values, not really important for this question. Suppose event A is taking 15 or more minutes to get to work, and event B is taking less than 15 minutes. Events A and B are said to be complements. Now, what is a complement? A complement is everything but the event. So something plus its complement would need to add up to what? Something plus its complement would need to add up to what? Something plus its complement would need to add up to 1. So think about this. You either take 15 or more minutes to get to work or less than 15 minutes to get to work. And you can say if I don't get to work, it took me more than 15 minutes to get to work because I never got to work. Or it took me 0 minutes because I didn't get to work. But is that everything that could occur, Kaya? You either take 15 or more or less than 15 minutes. Is that complements? Because complement is like you either have this or not this. Like it either takes you 15 or more minutes or less than 15 minutes. Would that be a complement, Tamara and Kaya? Either takes you 15 or more minutes or less than 15 minutes. Are those complements? Don't worry about being wrong. Just give it a shot. What do you think? Are those complements? Yeah, definitely. Yeah, they're complements. Don't worry if someone says no, then they are complements because they both can't happen. You either take 15 or more minutes, like you cut this divider here, or you take less than 15 minutes. So one of those two things must occur. They're complements. It's everything that can occur. You're either going to take 15 or more minutes to get to work this morning or less than 15 minutes, and they don't overlap. They are complements. When thinking about events with combinations of outcomes, things are simplified if individual trials are independent. Roughly speaking, this means that the outcome of one trial influences or changes the outcome of another trial. So independent means one trial occurring influences the other trial on whatever. Like if you flip a coin, the next coin flip will be influenced if they're independent. Like independent coin flips would be influenced. Is that what we're talking about? What are your thoughts on this? So it says, when you think about like flipping a coin, which is independent trials, roughly speaking, this means one outcome, like the first outcome of a coin flip, which is a trial, will influence the outcome of the next trial. That's what independent means. Is that what independent means, true or false? What do you think? Is that what independent means? We'll do one more version of this. No, that's not what it means at all. Actually, it means it doesn't influence it. It's very false. It's very false because what independent means, we'll go to the notes we took today. Independent means, and we took some really good notes and some examples, it means does something influence it? If it does influence it, they're dependent. If it doesn't influence it, they're independent. So we took these notes today with examples like, it's 75 degrees out. Does that influence what you think about snow? Yes. So the snow would be dependent on temperature. Then we did other examples here where if I know Brian had coffee, do you think Chelsea would be less likely to have coffee? And you would say yes, because she's my wife. But my brother, who doesn't live with us, you would say no, he's independent of Brian drinking coffee because it's not going to influence what you think. So this would be false right here. It should be have no influence, do not influence. Independent means they do not influence each other. Here we go. This one usually gets people. This is a mathier one, and it gets people all the time. So this one requires actually a lot of work to do it, so let's solve it, and it actually goes towards doing MyPearson questions. So you have to work on, where's it at? Leo knows.
Notation, brother.
Notation, brother. You're going to hear that a lot for the remainder of the semester. Notation. Why is this beyond the screen? Okay. So what I'm going to write right here is the following. And it's either a success or a failure. How should I mark, what should I write for success? How should I write the probability of a success? How should I write the probability of a success? Or failure? I've already done success. So how would I write the probability of failure? Like with the same notation, I've just abbreviated this right here. The probability of a success is this. That's what's been abbreviated down there into notation. How am I do probability of failure? Because it's either a success or a failure, complementary events. So we're using rule 3, complements. So how am I going to write probability of failure? Once again, don't even read their question. Just start taking notes. Boom, Tamara right there on fire. Yep. So first thing you do when you get a question like this is you just start writing down what you know. Does that make sense? Like we'll jump into the question here, but you write down what you know, and then you start working with the knowledge you have because you get more components and more information doing it this way right here. So it says the company is rolling out 5 new campaigns, which it should say are independent of each other. What is the probability that at least one is a success? The probability that at least one is a success. So when you think about the probability of at least one being a success, let me write this for you. This is where people get stuck, and we're going to call this at least one problems. And I'm going to even put this in the notes right here. Close out of this file. Don't save. Don't save. Solving an at least one problem. Probability. Chapter 12. Solving at least one problems. So you write down everything you know. And to solve an at least one problem, you want to do the following. Write your sentence. That's what a lot of people fail to do. I'm going to write down this. Either you'll have at least one success, or what about the campaigns? So you think you're rolling out a bunch of campaigns here. Either at least one will be successful, maybe 2 will be successful, 3 will be successful. So either at least one of the campaigns will be a success, because you've got 5 campaigns here. You got your 5 campaigns, and it could be that one's a success. These are failures. It could be that you had 3 successes and 2 failures. Tamara, you've done it. You're either going to have at least one success or all failures. You could say no successes or things like that. Like that means the same. Are you following with me on this? You're either going to have at least one successful campaign or all failures. Like one of those things must occur. If one of those things must occur, what is the probability of this? If one of these things must occur, the probability of at least one success or all failures is what? The probability of at least one success or all failures is what? Because one of these things must occur. If one of these things must occur, then the probability of it is what? 1. Because we actually just did complements and wrote a sample space. So if you go down here to what complements are, if we say like either you're going to have at least one success or all failures, well, those are complements. And now when we say the word or, we can actually use the what rule? The addition rule. So the addition rule is when we say the word or, we can add together 2 things if they're disjoint. Disjoint means if one thing occurs, the other thing can't occur. We also did some testing on disjoint knowledge right here. I know A occurred. Can B occur? If the answer is no, they are disjoint, i.e. mutually exclusive. They're the same word up there. So you can't have all failures and at least one success. So this means they are disjoint, so we can add them. We know the probability equals 1 because they are the complements of each other, creating a mutually exclusive sample space. Mutually exclusive meaning if one happens, the other can't happen. So you know what we can do? We can change this to plus, and then what do? We just algebra this over to the other side, and it becomes a minus. So you're just going to subtract this from both sides and algebra to this side, and you can see here the probability has been found. So what's the probability the first campaign is a failure and the second campaign is a failure and the third campaign is a failure? I moved around a bunch of things. Yeah, I moved. It is moved. Did I not move the quiz too? I should move the quiz also now. What is the probability the first is a failure and the second is a failure and the third is a failure? What is probability the first is a failure and the second is a failure and the third is a failure and the fourth is a failure and the fifth is a failure? What's the probability of failure and failure and failure and failure and failure? What's the probability of that? Tamara, excellent work. You are correct. Because they're independent, so we can multiply them together, at least assumed by the problem. So you merely just go here and use the multiplication rule to do the probability the first is a failure and the second is a failure and the third is a failure and the fourth is a failure. And so you just substitute in the mathematics of this right here. And you get 0.7 raised to the 5th power. And there it is. So the answer is 1 minus 0.7 to the fifth power, everything but all failures. 0.7, 2, 3, 4, 5, and then 1 minus, and there's the answer right there. Try writing this out. I know you're seeing some answers, makes it easier, but you want to be able to write these out and do them. I think we did some of the hardest questions. We could do this again. It's due on Friday, so we got more office hours before this, but let's do the quiz. Which quiz question are people stuck on? A lot of people are saying the quiz. Which quiz questions are people stuck on? Start telling me. It might be the blood type one, might be the M&M one, might be the soda pop one, or the light bulb one. Those are down here further. Might be the... I'm trying to think what else there is. Those are the big ones. I've done them a few times. Which ones should we do? That was in at least one problem, which is like the light bulb and the soda pop one. BS474 association rules. Can you explain more on the question 1 on the choose function? Yeah. Is it the choose function? It's on the practice quiz, right? Yeah, I think you trying right there. Let me go find that. It's on the, you talking about the practice test? Let me go over here. 201, grab a question. On the homework. On the homework. Oh, yeah, on the homework. Okay. Let me go grab the homework. So choose is looking at how many combinations of things that can occur when you look at the choose function. I'm going to pull up R here, and we got some more questions. Okay, pull it up. We just did Canvas content. Yep. We just got Canvas content done. We can do another version of the Canvas content. We're probably gonna do the quiz here, but whatever questions you have, we could do the quiz again or the Canvas content again. So with this right here, what we need to look at now when we use the choose function. Choose works the following way. It's a base function right here, and what you have right here is you're choosing. Got to make sure I do it in the right order. Ready? Perfect. This is saying if I have the American Red Cross, you got it, Jordan. Thank you, Daryl. So this is saying if I have 10 people I need to select for a party and I want to select one of them, I could choose it 10 different ways. If I have 10 people to invite to a party and I want to select 2, I could do it 45 ways. This might be easier to think if you only have, let's say, 3 people. If you have, let's do 4. If you have 3 people and you're inviting one person to the party, how many ways can you invite the people to the party? You're going to have 4 friends and you're only inviting one to the party. How many different ways could you do this? You have 4 friends and you're only inviting one to the party. How many ways could you do this? This is what the choose function tells you. You have 4 friends, 4 ways. So very clearly, you could select, you got 4 friends. That friend looks like they're ready to party. Got your 4 friends. You could choose this one, way 1, way 2, way 3, way 4. And we can do more version. A lot of people say more Canvas. Can we do one more? Yeah, we'll do one more Canvas content. And then we'll do the, yeah. And let me put this in the notes, the choose function in 474. So 2030. BAS 474, choose function. Okay. And so now if you look at 4 choose 2, what 4 choose 2 is going to say you have 4 friends and you're going to choose 2 of them to come to the party. So how many ways can this occur? You can actually figure it out without writing the function. 1 way, 2 ways, 3 ways, 4 ways, 5 ways, 6 ways. Does that make sense right there, Tran? What's going on? Because it's going to say 6, and there's the 6 ways you could do it. It gets more complicated if you have like 5 friends and you choose 2 friends to go to the party. So this is the ways in which we can kind of group variables together if we're making a rule of 2 things and we're grouping together. That's the way it works for Market Basket. So if you have 5 friends, you're choosing 2 to go to the party. Wondering which one? The Canvas content? So you go right here. This is 1 way you choose 2 friends, 2 ways, 3 ways, 4 ways, 5 ways, 6 ways, 7 ways, 8 ways, 9 ways, and 10 ways you could choose 2 friends. So we run this algorithm right here. You get the 10 ways you could choose 2 friends. How's that looking, Trend, right there? Is that making sense with the choose? I don't want to quite give away the answer, but that's what the choose function does. Is it tells you the unique combinations by which if you have 5 things, you could select 2, or the unique combination, it'll also be 10 right here, I believe, because it's symmetric. The unique combination, if you have 5, because now you're excluding 2, because it's kind of the same idea of instead of selecting 2, exclude 2 if you're selecting 3. Is this making sense, Tran, on how this function works and what it tells us? The choose function tells us out of how many things, n, we want to select k items, and how many ways in which we could do this. We use this for rules to say if we have like 1,000 items at a grocery store and we're making rules of length 2, how many ways could we make these rules? A lot. The answer is a lot of times. Let me know if you still have questions on this, but that is what the choose function does. It allows us to figure out the kind of combinations of which ways we can choose things using the amount we have and the amount we want to select. Okay, let's do another version of the Canvas content. Please, if you have more questions, let me know. I will clarify. I will go into more detail. And then we'll do the Canvas content one too. I understand the choose, however, I don't know how to apply it for length 3, which is 2 for the antecedent and 1 for the consequent. Is this correct? Choose number of... Let me look at the question specifically before we go over here. Let's look at the question. Let me look at the exact question. Thank you right there, Tran, for asking. Fall Cindy Fall. Okay, association rules do not. Okay. RMD. How many bands have at least 80 listeners? How many bands have a support of this right here? If we consider only rules of length 3, if A and B, then C with these bands, use the choose function to determine how many possible rules exist. So basically, we are selecting 3 right there, and we have from these amount of bands right here. So we need to figure out first how many bands there are, and then we need to figure out if we're making rules of length 3 right here, which can have that we are selecting 3 of these things right here, how many possible rules exist. So definitely check that out right there. I don't want to give away the answer, but does that make sense? Oh, did someone, I don't know, mute up her or something or not. But first you want to figure out how many bands have at least 80 listeners by looking at the support. You can also do the item frequency, we'll find that. So item frequency will find this. And then if we're doing rules of length 3, we would have to use the choose function to determine the amount of possible rules, and then we would choose 3 right there. Kind of, sort of, maybe. I can't quite say, but maybe. So, don't worry, Mubot, Tran, don't worry, Mubot's just getting mad at, he thinks it's links, but it's not. I think it's the dots. Mubot, he doesn't even remove it. Well, that's not good. He's supposed to remove it, but he's Mubot, he doesn't know. Mubot just getting mad. Let's do another Canvas content. I'll throw you some points, everyone, for Mubot throwing a temper tantrum in the chat. He's very testy today. Canvas content. Help me out, everyone, with the Canvas content. Canvas content number 6, chapter 10 and 12. The purpose of a sample is to have enough data to accurately describe the sample statistics. Yes or no? What do you think? The purpose of a sample is to have enough data to accurately describe the sample statistics. Yes or no? Why or not? That's all right. Don't worry. 1,000 points. Don't worry. 1,000 points. It is false. The purpose of a sample is to understand the what. The purpose of a sample is to understand a what. Why did we make inferences into this? We collect samples to understand what's, because they're the thing of interest. The thing we care about. That's why we call it the this of interest. We're interested in it. We take samples to understand what's. I'll double check. Tran, I'll double triple check. I'm gonna look at the key in a little bit. So I think I have the key for it. I'll double triple check. You're right with the ordering. Understand the population. Very true right there. With the ordering of it, the way in which, let me look at the question again. The way in which we pick them, right? Because choose doesn't do it with respect to order. It's just going to pick like 3 things. And it doesn't do it with respect to order. Because I think even this question might be a little misworded. It's just to point out there's a lot of rules. But to say that it's kind of why do we need the a priori method, the a priori learning method. So I do think, and I might point this out to Dr. Liu and Dr. Brian, is that I do think you're hitting upon a theoretical quandary on this, that it's going to put like A, B, C, and then it's not going to do the ordering of it. And I think you are correct, Tran. So let me double check, because truthfully, what you would need to do is for each way, and I need to see if students are also answering it this way, for every possible rule, you would then have 3 more ways it could occur, because it should be then times 3 technically. So you might add in a technical answer, and then let us know if you get it wrong. Because think about this, if we choose A, B, C right here with the choose, like we said with the friend example, and thank you, Tran, for making me think through this. I'm like, wait a minute here. Because when you say the antecedent and the consequent, it could be that the fourth friend is the antecedent, but if we switch it around, the fourth friend could be the consequent, which is the end of the rule. Is that what you're thinking, Tran? Great job. I was like, wait, you're right. And then I need to check the key. So technically, I would add in a technicality here. You could say there are this many ways to select items, and please let me know if you get it wrong. Talk to me. I'll talk to the graders. I'll also probably tell them to update the key if the key has an issue. To say that there's the technicality that the ordering actually matters on what's on the antecedent and the consequent. And since we're selecting 3 things, it wouldn't matter if we said A, B, or B, A, because someone else might be thinking, what about A, B, C, B, A, C? That doesn't matter, Rock knows. Because the antecedent is A, B in the card or B, A in the card. It means the same thing to have A, B, or B, A. But what matters is what's in the consequent, if it's BCA or ABC, because then how does BC being in the card affect A, or how does AB being in the card affect C? But AB being in the card affecting C is the same thing as BA being in the card. So to visualize that, and thank you, Tran, for so much asking this, AB in the card affecting C is the same thing as BA in the card affecting C, which is not the same as, which would not be the same as CA in the card affecting B. So really what you have is additional 3 ways of doing it. So really good work. Another 5,000 points. Everyone give some W's for Tran in the chat right there. Making me think. Make sure you get the points if you're doing it that way, because I don't want you to get it wrong because maybe we didn't think it all out. We're like, wait a minute. There's always a little extra to it. The blank is a list or collection of things of individuals from which the sample is drawn. What is the list or collection of things that we draw from to create our sample? It's the ones we can draw from. Which one is the answer here? What can we draw from? We did the next one already. What can we draw from to create our sample? It's kind of 2 answers here. I could see how someone would pick the other answer. Hopefully I don't get anything wrong. Yeah, exactly, Trent. Just let me know if there's issues. Let me know if there's issues with the grading. I'll fix it up. There shouldn't be, but no, really good points and really good comments. What is the list of individuals or collection of things that we draw our sample from? Specifically what we take the sample from. It might actually literally say it this way in the notes. I bet it does. Oh, yeah. Law of large numbers. What is the answer? The list of individuals or things from which the sample is drawn. Now you just have to read the screen. What answer does it want you to give? Sample frame. Yep. The population is everything. It's not what we draw. I mean, you do technically because the population is everything, but the sample frame is what we can take our sample from. We did this one. Check out the previous video where we did it. We did this one and we did this one. Let me see if I can get, I think Daryl's giving one from the quiz. We should have a 10 out of 10 here. 10 out of 10. I miss one every once in a while. Let me see if I can get that one, Daryl, and then we'll hop over and do the... we haven't done this one yet right here. We haven't done both of these. A researcher wants to examine grams of fat in milk. They get 2% milk and low-fat milk and randomly select cartons to measure the fat. They put the milk into groups, acknowledging differences between whole-fat milk, 2% milk, and low-fat milk, and they select within those groups the sample. What kind of sample is this? So they're going to say, like, okay, we've got like whole milk, 2%, and low fat, and we're going to select samples from within those. Oh, we could do that one too. There's the bus arrive on time. Jordan and Daryl got the 2 tougher ones. We'll try to find those. We'll do those, and then we'll, yeah. So what kind of sampling is this? Don't worry if you get it wrong. What do you think it is? Hint, they are acknowledging differences. They are acknowledging differences. They are acknowledging differences. That's the big hint. Like they're saying, okay, we're going to have this type of stratified. They're not taking all of one group. So when you cluster sample the clusters, you take all of a cluster. When you stratify, you acknowledge differences and you say, like, we've got this type of milk, this type of milk, this type of milk, and try and getting those points right there. We got a bunch of points from that. So if you go back to the notes we have right here, at the very end, we talked about a clustering scheme. Did I delete it? We talked about different clustering schemes, but check out the notes from today where we did that. Okay. A sample frame is everything that could occur. So if you're having two children, sample frame right there. Order does matter in sample frame. Literally pretty much doing what Tran was doing just a moment ago. Suppose event A, we did this one. In probability, the value of each trial is called a what? What happens at each trial is actually called a what? Is it called a consequence? Whatever happens in a trial is called the what? You flip a coin, it has a what? Who remembers for 1,000 points? And we'll try to find these other two questions that we haven't done yet. When you flip a coin, it has a what? Whatever. I have to say the word. It's an O word. The value of each trial, like whatever happens in the trial, is its something. Any guesses? I want you to remember the words. You remember it, it sticks more in your head than me saying it. Outcome, Daryl. Yep. That's false. You said the right thing, Daryl. We want to understand populations, not samples. I mean, like, you understand what did I get wrong? What did I get wrong? Oh, they are complements. Sorry. We did that one earlier, and I explained that they are complements. So, here we go. Law of large numbers. Okay. Let's map this one out. You are headed to the Law of Large Numbers Casino. You're going to do a little gambling. And here we are. What is the probability you get a lemon and a cherry and a bell in that order? And this question should say in that order. Now, when you think about a roulette, like a slot machine, each wheel is what of the other wheel. So if you get like a lemon, each wheel is what of the other wheels. Each wheel is what of the other wheels. Each wheel is what of the other wheels. Independent. So each wheel is independent of the other wheels. So as The Rock would say, it doesn't matter that you got a lemon on your first wheel. The next wheel is going to have the same probability of it. So what's the probability right here? And what word do you notice between all of these? What word when I say you get a lemon and then a cherry and then a bell? What word? And. We see and right here. And what does and mean? It means multiply if things are independent. And this is where huge notes to have, and also your formula sheet will show you that if two things are independent, you can easily multiply them together. Notice and is right here, and we have multiply between the probabilities. So all we need to do is start listing the probability. Well, the probability of a lemon is going to be 3 out of 10. The probability of a cherry, we'll put it down here, 3 out of 10 probability. Probability of a cherry is 2 out of 10. The probability of a bell is 1 out of 10. And we can multiply these together because they are independent, leading to a probability of 6 over 1,000, i.e. 0.00. Whoops, one too many zeros. I hate it. It advances it back to the top of the screen when I do that. 0.006. No, I think it's one more. Let me think. That'd be 10,100,000. That's right. Okay, hopefully I'm doing it right. Okay, let's go back over here. Yeah. I've done it right. There, why doubt yourself? Never doubt yourself. Why would I do that? Why would I doubt myself? So there's the probability right there. Probability of getting all three of those in a row. Great job, Daryl. Yeah. And sample space, boy, 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 girl, girl, boy, girl, girl. And here we go. We did the marketing campaign one already. Let's go find the bus one. The bus one is another at least one problem. I think I missed one of the questions. That's all right. I missed question 1. Population is what we care about in differential statistics. Find the last question right here. Here's the bus stop one. So this is in at least one problem. So before you even do it, we're going to say the bus is late or on time. So what should I write for my notation? This is how to do these problems and get them right on the test. So we have, what should I start writing with my notation? Tell me what I should write to start. If you don't know, it's all right. Just take some guesses. This is how to do these problems and get them right, because these are just a process. You have to know the rules of writing down probabilities, then finding complements, and then also writing your sentence, which are complementary events, which add together to one, and then doing the multiplication rule, and then you can solve these. It requires pretty much knowledge of the full chapter to solve this one. It's a very short question, but it says, what is the probability the bus is on time for at least one stop? And assume independence, which is a big assumption. So what should we write to start? Any guesses? We'll do American Red Cross one after this. Very similar. What should we write to start? The answer where we're going to start is right up here. So what should we write? We want to first mark our notation.
Notation, brother.
So what should we do? I'll give it another second or two, and then I'll give some answers. Nice. Daryl, very close. So kinda, sorta. We're going to write probability OT. Probability on time is equal to 54%. And then probability late is equal to 0.46. So we want to write probability on time is this, and probability of late is this. Now we want to write our sentence, and this is usually where people get stuck, and if you do a bunch of these, you just get used to it. So I suggest doing these because you'll get used to it and it'll be very easy. And then, yeah, because probability, and then probability of what? Because the P just stands for probability, and then in the parentheses is probability it is on time is 50%, probability is late is 46%. And now we write out our sentence where we say the bus is either on time at least once or what? The bus is either on time at least once or what? The bus is either on time at least once or what? It'll either be on time at least once or what? And this is actually what we want to find. We want to find the probability of on time at least once. That's what we're looking for. So it's either on time at least once or what? Not at all, which means always late. Does that make sense? And then what do these probabilities add up to? Well, they can't occur. They're complements. They add up to 1, and we shouldn't have the on time at least once or always late. And then we just go here, delete this out, and then we change it to a plus. And now we just have to figure out the probability of always late. And when we look at the probability of always late, how do we figure out the bus is late to all 5 stops? How would we figure out the bus is late to all 5 stops? Like it's late to the first stop, and then late to the second stop, and then late to the third stop. You hear the word I'm using? And then late to the 4th stop, and then late to the 5th stop. What is the probability it's always late? Because if we figure out this, we can just do 1 minus the probability always late. And then we'll have the answer for it's on time at least once. What is the probability of it being always late? Yep, Kaya, nice job. I mean, you just take the late right there. Kaya, did these seem a lot easier now? Like, there, and there's the answer. That's it. You can just go 0.46 times 2, 3, 4, 5, and 1 minus. It's probably going to be on time at least once. Yeah, and then 1 minus. So you just do 1 minus that. Once you do a bunch of these and you do the steps and you see how to do them, they're a lot easier. This chapter is so mathy. So 3 decimals, it'll be that right there. And then when I do them, I fear people are just like, that's the answer. And then they don't solve it. I'm like, no, you have to practice. You have to know how to do them. You have to understand it to some degree. Let's go do that Red Cross question. That is a tricky one. Did I find it? The American Red Cross question. There's another at least one problem. These can be... We did that one. Oh, here we go. Red Cross. I knew it was towards the back. Okay. This is a very good question too. Uses the addition and multiplication rule a lot. So fall 3. And this is chapter 12 quiz. American MyPearson. MyPearson quiz. The American Red Cross. Okay. So what do you think we're going to do first? Before even working on this problem, I'm going to write down all my whats. Before even working on this, I'm going to write down all my whats. This is what you need to start doing on these problems before you even work on them. A lot of people just jump right in and say, "Oh, I'm gonna solve this whole problem. I'm gonna do it all. Write down all the probabilities." So we have the probability of probability of type O is equal to 0.446. The probability of type A, please tell me if I get something wrong, is 0.396. That's a 3 if you can't tell. And the probability of type B is equal, running out of room on the screen right here apparently, is equal to 0.114. And these are all the blood types except probability of AB. So how do we get the probability of AB since it's the missing one? And this would be all the blood types that exist. You can be positive or negative, whatever, but O, A, B, and AB, as far as I know, are all the blood types. So how are we going to get probability of AB? Because this is the sample space, is everything that can occur. So the sample space would have to add up to what? 1 minus all, exactly. So even though it's not asking us it, we can go through their questions or we can start to think. We don't have it yet, so we're just going to take 0.446 plus 396 plus 0.114, and it's going to be 0.044. So we can double check. 1 minus that, 0.044. There we go. 0.044. Hey, what's up, Nate? Good to see you, Nate. What's between complete linkage and single linkage and hierarchical clustering and in k-means? Complete linkage always carries the longest distance, where single linkage always carries the shortest distance. So if you have points like, there's a good graphic on this. I'll show you right after this one. I'll keep this. I'm going to pin this message, and I'll do it right next after this question. You got it, Nate? Pin message. Okay. So what is the probability of AB? We just found that. What is the probability that the donor has A or B? Now, are these blood types mutually exclusive? Yes, no, and why? Are these blood types mutually exclusive? Yes, no, and why? Mutually exclusive means if you have one of the blood types, you can't have another blood type. They're like, hey, this person's blood type O, but they're also blood type B. They are mutually exclusive, which means we can add them. If things are mutually exclusive, you can add them. So all you'd have to do for this question right here, question 2, is just add together these probabilities. Just add together. What is the probability they're not O? They're asking for the what of O for this question right here. This question is asking for the what of O blood type. It's because what's probably they're either O or not O. So if their probability of O is this, what's the probability of not O? These are the easy ones. So they're just asking for the what of it. So good to remember the terminology here, because if you say not this, you're just asking for the what of it. It's like good work, but with an E instead of an I. Complement, the complement. So we can figure out these probabilities pretty well. The probability of AB is 0.044. Probability A or B is the last two added up, I believe. I think it's A or B right there. So it's going to be 39, and it wants to decimals. Good. I think I just typed it in wrong. I don't even know how. 396 plus. There we go. And then not O is the complement of O, which is going to be 554. And I don't want to get anything wrong, so we'll double check. So 1 minus 0.554. Yeah, there we go. You can complement the complement. And so now, here we get to the tougher ones. There are 4 donors walking in. What's the probability the first is O and the second is O? See you, Daryl. What is the probability? We'll have off start tomorrow. You got it. What's probably the first is O and the second is O and the third is O and the fourth is O? Who knows that in the chat right now? What's probably the first is O, and the second is O, and the third is O, and the fourth is O? Who's got that? The first is O, and the second is O, and the fourth is O. Nice thing. The first is O, and the second is O, and third is O, and the fourth is O. What's probably first is O, and the second is O, and the third is O, and the fourth is O? Notice I'm saying and between all these. I'm saying they're and, which means we're doing what? We're multiplying probabilities. So when you have this right here, the first being O is 0.446, and then the next is O, 0.446, and then the next is O, 0.446, and then the next is O, 0.446. Assuming they're all independent individuals, the probability is going to be 0.446 raised to the fourth power for how many people walked in the door. So that one's an easy one right there. The probability they're all O is going to be 2, 3, 4, just 0.446 raised to the fourth power for 4 donors. Make sure you see how many donors there are. And round to 3 decimals. There we go. The probability that no one is AB. Now this is where it gets tricky. Remember, we figured out the probability of AB is this right here, 0.044. So we need to write our sentence again. And our sentence is going to be, it wants no one is AB. Oh, that might not be that hard. Probability of AB is 0.044. Probability of not AB is equal to the complement of it. And the complement is going to be 0.956. So the first person is not AB. And then how's this looking? What is chat thinking? Not AB, and then not AB, and then not AB. So all we do here is 0.95 times 0.95, 6956. It's going to be 0.956 to the fourth power. But that is the mathematics going on right here to figure out the first is not AB, and the second is not AB, and the third is not AB, and the fourth is not AB. Because we just had to figure out the probability of them being not AB, which is 1 minus AB, and then we had to say the first is not AB, the second and third and the fourth. Ooh, I think I did 5. I heard a fifth. 2, 3, 4. There, I did do 5. Double check your work. You can Google it. Type into Google, what is this raised to this? Good way to check too. And there's the answer. The probability that they are not all type A. Wait, the probability that no one is type AB. Good. Yeah, no one's type AB. Just worded weird. What is the probability that they are all not, that they are not all type A? Well, they're either all type A or not all type A. Did everyone hear that? They are either all type A or not all type A, which is what we want to figure out. And these are complements. So we would change this right here to the addition because they're complements. And we are trying to figure out they're not all type A. So we need to do 1 minus all type A when we algebra this over. The probability of type A, I think I still have over here. Type A is 0.396. So that would be every single person out of the 4 of them are all type A, which is 0.396 raised to the fourth power to get the probability of not all type A. Once again, this is another at least one problem. Not all type A, meaning at least one person is not type A. So that would be the mathematics, and we just solve out the equation. 0.396, 2, 3, 4. And there we go. There's the probability. Very likely that they're not all type A. As long as I haven't done a math error, we're good. The probability that at least one person is type B, and this is a similar question. So at least one person is type B would be the following. It's very similar. So at least 1B, you can just change this, at least 1B. And then no one is B. So either at least one person has type B blood or no one has B blood. And so we go right here. We change it to the math. And remember, we're trying to find at least one person is B. So we're going to algebra this over to the other side that no one is B blood. And that's going to lead to the equation over here. And once again, writing this sentence is the key, as the thing just wants to make it look weird. And so the probability no one is B, the probability of B blood is 0.114. So the probability of someone not being B blood, probability of not B blood is equal to the complement of that. So we go here and do 0.886. We double check our math to make sure, even though we can do mental math. 1 minus the probability to get the complement, and there it is. So it'd be the first does not have B blood, and the second does not have B blood, and third, so 0.886 raised to the 4th power, not the 54th. But that should do it right there. We should get it all correct. 2, 3, 4. 1 minus, and there's the probability. And these can be tricky. This is a tougher one. Watch me make one error. Got it. Awesome, Nate. Let's talk a little 474. It's got a really good question right here on 474. 5413. BAS 474 clustering. Okay, let's bring up some notes and talk over it. And here we go. Okay, I'm going to copy the question right here. Hey, Brian, I like it. Okay. What's the difference between single complete linkage and hierarchical clustering scheme and in k-means versus hierarchical when we might prefer one method? Really, the question, last one's very theoretical and really tough to answer. The first one is very clear answer, and I'll explain why. So if we have a very, very small example of data right here where we have a grid of data points where maybe we have this point, and this point right here. We'll call this point 1, point 2, point 3, and then we draw out the distance matrix between these. So what you'd be looking at here is we always put this in the center because you can't have a distance from yourself. They're all kind of closest difference. We'll put some numbers here, like 1's distance from 2, which we're currently looking at this. 1's distance from 2 is going to be like 6. 2's distance from 3, we could do 2 from 3, why not? Is a little bit bigger. So we'll say that that's 8. And then the distance right here, we got to do the other one, 3 from 1, 3 from 1. That's also kind of bigger. Let's say that's 7. Just keep the numbers kind of easy to look at. And this is just how far these values, these points are from each other in this multi-dimensional space, or this bivariate space. And so now what we need to do here is we need to choose if we're going to do single, complete, average, or wards. And we're really only going to focus in on what happens when we do single and complete. We've never made anyone do the average right here, but that is a way of doing it. And also wards is a little more complicated. But the reason you pick these is because when you recalculate the matrix, the calculations in the matrix will depend on what you pick here for the next row of calculations. If we go down here, like obviously what is going to merge right now is going to be 1 and 2. 1 and 2, will you always merge on the smallest? Exactly. Complete doesn't merge on the largest. You always merge on the smallest. So no matter what happens here, 1 and 2 will merge. And so if we do single, 1 and 2 merge. 1 and 2 merge no matter what. Good questions, Nate, right there. So 1 and 2 merge. So actually it's going to be very small. We only have 2 merges on this. I hope my example works really well. So, because I want to make a small matrix. Actually, I could probably do average. It's not that hard with this few. Okay. So with this right here, what we're going to do is merge 1 and 2 into a cluster because you merge on the smallest. So this is a cluster 1, 2. And now we have 1, 2 over here. Its distance from itself is not going to be used. And then 3, and 3, and 3, and 3, and 3. And once again, we don't put numbers in there because you can't have a distance from yourself. And we only have 1 more value, so the average is going to be very similar. So you are going to see a difference here, though, because since 1, 2 is merged, if we do single linkage, when we look at the different distances here of 1, 2 from 3, we will carry over what number? Since we're doing single right now, the matrix is recalculated using the what number. So since we're doing single linkage, the matrix is calculated using the what number. Actually, these will all have differences. The matrix, it will be showing the new distance as what number? 7. Single uses the smallest distance. But now on complete, the matrix is going to have what number in it. This is just how you calculate distances. Like single, complete, average, or wards just is how you calculate distances. It's not, you always merge on the smallest. Using complete, it'll have 8. And then the calculation here of the distance will be what on average, which it's the average, which will be really messy if you're dealing with a big data set. But right now we can figure it out. I can see it. There we go. This is the average of those. So that's what the average means. So the reason you choose between single, complete, or average is it determines how you recalculate the matrix. Great job, Nate, right there. Does that make sense? Like the way you recalculate the matrix depends if you're doing single, complete, or average, where single is going to choose the smallest distance, complete is going to use the larger distance, average is going to do the average, and wards is going to do the sums of the squared error between the, like trying to reduce that. So I've never calculated that one by hand. But no matter what happens, every time you merge, you're always going to merge on the shortest distance. But then when you recalculate the matrix, how far away things are depends on the way you choose to do the calculations. Does this example make sense right here, Nate, on like doing the calculations again, like seeing the kind of steps? Like if you were to recalculate the matrix, you wouldn't do all these calculations. And your next one's kind of really good on the theory behind it, because you asked theoretically, and in k-means versus hierarchical clustering, which one might you prefer? Do you know when to use single or complete? The thing is, here's what you would do. You literally, when you do these algorithms, you run it a few times till you get a good dendrogram. So when you run the algorithm, if single linkage gives you a dendrogram that looks, shoot, I'd go find some pictures. Dendrogram. Okay. Looking for certain dendrograms. Why are they all so pretty? Oh. I think someone's here. I'm gonna tell them. Oh, finishing all his hours. Oh, there you go. Let me see right here. Copy image. Okay. Random dendrogram picture. Copy image. Here we go. Dendrogram. This is a beautiful dendrogram. Trying to find a messy one. Is no one posting messy dendrograms? I might have to go make a messy one. Yeah. This one's not horrible. This one is so beautiful right here, Nate. They used wards distance. They even show it down below. Yeah, I wouldn't be rerunning it. How many clusters do you think you would have if you ran your clustering algorithm and you got like this dendrogram? I'd say there's 2 answers. So how many clusters do you think you would say you have? I think I have on in-person office hours actually, right? Ours says I'll head over there after this. How many clusters? I wouldn't go for 4. Good answer. At least 30 some points. 4 would be if you cut. You'd have to cut here for 4, and that's a hard area to cut. It's much more likely you'd probably have, if you're cutting, either 3 or 2. There's really good separation here with 2, or 3 has good separation. You have to get some clear space to cut, and the cut spot for 4 is a little tougher, like right in there. This one is not as clean. You might rerun this. You can see the 2 space and the 3 space. It might be 2, or this one could be 4, because the 4 space where you could cut and make 4 exists like this. You want a good open area where you can cut. There's not really a good 3 space in here, and then the 2 space where you could cut and get 2 is pretty large also. So the answer to this one's probably 2 or 4. I mean, there is no answer to this unsupervised learning, but you really want good clean area because of the 3 space. Does that make sense? Like this one, probably I wouldn't make 3 with. It's also not as clean because you don't have as obvious. Oh, finally. Well, this one's not as bad. And they're cutting here to make 3. Let me see if I agree with their decision. And they'll head over after this. I might go for a 2 clustering scheme. So here, you might just go and cluster on 2, but there's no answer. You could just cluster on 2. That dendrogram it's not as horrible. I've seen worse. You just rerun it and see if it gives you meaningful clusters. And if it gives you meaningful clusters, you use it. If it doesn't give you meaningful clusters, you don't use it. This is a really good example here. Which of these two clustering schemes looks cleaner to you, the left or the right? Oh, it says random data. Yeah, I guess it is random data, right? Hence, this one over here on the right actually looks worse because it's random data that actually probably has no relationship in it. And this one over here has a cleaner, like maybe you could cut in here or something. Just depends on where you want to cut. The one on the right is merging together pretty quickly at the top. This one has some merging at the bottom and then makes some clustering. So you just rerun your dendrograms until you get one that looks pretty good and gives you meaningful clusters, because there is no right answer. This one right here doesn't really have a good answer to it. I've seen a lot of dendrograms. This dendrogram, not such a great answer, and they're probably trying to point out something weird with the data structure. Where I just saw one a second ago, this one right here, looks like one I've done before. Oh, no, it's just seeing one thing. This one has a more obvious answer of probably two. Well, Nate, that's got it. I'm going to head over, do some in-person office hours. With that, good work. Let me know if you have questions. I'm just knocking things around. Let me save the notes. The probability that adult male has high blood pressure. We will come back, Jordan, next. I'm going to do in-person office hours here, but we'll be doing it next time. Until then, bye for now, everyone. Bye. Stop streaming. We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.